satisfy the diffusion equation, okay? You satisfy the diffusion equation with the source term, okay? But there's another thing that we need to prove that U is indeed the solution to the diffusion equation with sources, which is that the U should also be consistent, okay, with the initial condition. How to prove that? We just need to show, or mathematically speaking, we can show that when t equals to 0, my uxt, okay, converges to the initial condition 5x. Okay? I need to prove that. But this step is actually very straightforward. Don't forget my uxt actually equals to, again, from negative infinity to positive infinity, right? And then the s x minus y t phi y, okay, dy, and then plus, okay, a double integral from 0 to t, and then from negative infinity to positive infinity, something that's about dy ds, sorry. Right? When t goes to 0, that's my second integral stand. When t goes to 0. That's my second integral just goes away, right? Because this is going to be the integration from 0 to 0. It's actually irrelevant. So we only need to focus on, okay, this. We only need to focus on this. So you see, when talking about the initial condition, the source term is completely out of the equation. The source term is completely out of the equation. We are only talking about the initial condition. And in this case, which means that in this case, okay, by proving this, we are essentially also proving that, okay, even for a diffusion equation without the source term, okay, even for a diffusion equation without the source term, the solution U should also converge to the initial condition phi. Okay? Can you prove that? Can you prove when t equals to 0? Can you prove that the integration from negative infinity to positive infinity s x minus y t phi y dy, this goes to phi x?
Oh, this is just the same.
Again, exactly the same, right? Okay. Because the source term, again, when t equals to 0, the source term will be converging to the delta function. Well, actually, converging to a delta function, that's a very dangerous word. That's actually a very, very dangerous word, mathematically speaking. It's not rigorous at all, because again, delta function is, first of all, delta function is not a function. Second, delta function contains an infinity, contains a singularity. Okay. But don't forget, we talked about how you usually view the delta function. Delta function is the functional. Okay. The really important is what is happening when delta function is doing the convolution, or when the delta function is actioning upon other functions. So if we can be more tolerable over here, okay, this can be more as shown by the way, because again, the argument, the not so rigorous, not completely rigorous argument is that, okay, again, the source function is actually the delta function x, okay, delta x minus y and then phi y, okay, and this again is exactly my phi x. That's all. Sounds good? Okay, sounds good. Okay, so this is everything about the diffusion equation with the source term. Okay, I'm having 40 minutes now. I'm having 40 minutes now. What I propose is now that I first go to 3.5 very briefly, because 3.5 is very related to the issue that we have just discussed. I'm going to 3.5 okay, instantly, and then, but I'm not going to go through all the details of 3.5. I'm just going to tell you what is 3.5 about. After that, we will turn back, okay, to the last part of 3.3, which is when we are having the diffusion equation with source, but only on a half line. How do we deal with that? Okay. So, bearing this in mind, this is actually all these things, although it's only part of the proof about that U is indeed a solution to the source equation. Okay, U is indeed a solution to the diffusion equation with sources. Okay, but this is very relevant to the discussion in 3.5. So let me jump to 3.5 and see what's over there, right? Okay, so 3.5. 3.5. Okay. 3.5. It basically tells you about two theorems. Okay, it basically tells you about two theorems. So, theorem 1. Okay, theorem 1. Let my phi x be a bounded continuous function, okay, such that x is between negative infinity to positive infinity. So again, two things: it's bounded and it's continuous. Okay, so it has some good property. It doesn't exceed. It doesn't gross up to infinity. And second, it's always continuous. Okay, then. Okay. Then uxt defined as the integration from negative infinity to positive infinity. Okay, so as x minus y t phi y dy defines an infinitely differentiable function uxt where x and t belongs to, again, from negative infinity to positive infinity and from 0 to positive infinity. Okay? And uxt solves ut equals to k uxx and limit when t goes to 0, but this is I'm deliberately writing the arrow downwards, okay, not backwards, saying that now t only approaches 0 from the positive side, not from the negative side. There's only one way for t to approach 0, because t is defined to be always larger than 0. Right? T cannot approach 0 from the negative side, because t will be undefined in that case. Okay? And uxt equals to phi x for any x. See, it seems to be repeating whatever we have been talking about, right? So you see, if I have u to be something like this, then of course u solves the differential. U solves the equation. Okay, ut equals to k uxx, and the initial condition will just verify that, right? But you see, there are a lot of them. I mean, the whole chapter 5 is written in a more mathematical rigorous fashion. Okay, that's why you are seeing these terms bounded, continuous. Okay, in the conditions, and we're also seeing something like infinitely differentiable function ux, uxt. Okay, so here the first thing. So you see, so this theorem basically tells you that, okay, you do something like this, that u is a solution. But it also gives you the properties of the solution, uxt, okay? Which is that, first of all, if my phi x bounded continuous, but continuous doesn't mean differentiable, right? Continuous means that, it can be very rough on every single point. But as long as bounded and continuous, then the solution, okay, any of these roughness will just go away right away. Okay, will just go away right away. And the whole function uxt is infinitely differentiable, no matter on x or either on t. It has infinite order of differentiability. Okay, so this is very crucial. the solution to the diffusion equation is infinitely differentiable. And also, my uxt approaches phi x when t equals to 0. Okay, when t equals to 0. You see, here, and you may be a little bit confused. Isn't that true that we just proved that my u should approach phi x? Okay, is that right? But you see, again, don't forget what was my argument? My argument that you see, first of all, s at x minus y0 is actually delta at x minus y0. What is delta? Okay, we have never formally defined what is delta function. Okay, we just talked about the properties of delta function, and we illustrated the delta functions on the sense of the in the sense of integration and convolution. We talked about what is the effect of delta functions when they are actioning upon other functions, but we have never talked about what, because if delta function, if it is not a function, then what it is, right? If delta function is not a function, then what it is. Actually, the formal definition for the delta function can only comes from this, the case like, first of all, I define a space of the function. I define that, okay, a lot of functions, they belong to a linear space, okay? Since this is a linear space, I can define a dual space for the linear space, okay? Then the delta function belongs to the dual space of the dual space of the linear space of the function, because my delta function, it doesn't make sense at all when standing alone. The delta function doesn't make sense at all when standing alone. It's not a function at all. But it can only make sense when it actions upon a function. That's why it belongs to the dual space. That's why the delta function is called a functional. Okay, delta function is a functional. Delta x is a functional. Okay, and which means that it actions on functions and is always sending functions to numbers. Okay, and of course, this argument belongs to functional analysis, and I should not delve into this a bit for too much. But that means that whatever that we have talked about over here, okay, is not rigorous at all. Okay, it is not mathematically rigorous at all. We just said that, okay, so this can be approximated by a delta function, okay, and then the delta function action upon and convolution with phi is phi itself. Okay, that's it. Okay, we didn't prove anything. We just simply understand it in an intuitive fashion. Okay, and chapter 5 comes up with the theorem, okay, in a rigorous fashion. Even more, it also talks about that U is actually infinitely differential. That's why reading how to prove that my Ux really approaches the initial conditions when t equals to 0. And the proof is strictly restricted, okay, within whatever the knowledge that we already know for now. So it's good? Okay, so this is the theorem 1. This is the theorem 1 for 3.5. And there is another theorem. Again, I don't have time to get into detail here. I just tell you what is the spirit. And you should finish. You are supposed to finish the reading, okay, by yourself, because everything about that is just about integration, differentiation, and nothing that's actually beyond your Calc 1. Okay, I suppose this will be should be easy enough for everyone. Okay, and theorem 2. Okay, theorem 2. You see, in my theorem 1, I was supposing that my phi x to be a bounded continuous function, right? Which means that my phi x, although it is not so regular that's, for example, infinitely differentiable, but my phi x is more or less controlled, right? But you see, during our discussion of the diffusion equation, the initial condition it can be as rough as a delta function. then the next question is that when my phi x, when my initial condition is not so well defined, okay, if my initial condition is not so regular, for example, if it is not continuous, then what can I say? Okay, what can I say about the following solution? What can I say about the following solution? Then the theorem number 2, okay, is that let phi x be a bounded function that is piecewise continuous. Okay, piecewise continuous. Then uxt equals to, from negative infinity to positive infinity, as x minus y, t, phi y, dy, okay? This is, again, is infinitely differentiable, okay? But only for t to be larger than 0. Because you see, originally I was saying that the differentiability can actually involve, I didn't claim t to be larger than 0, right? So which means that originally the differentiability actually, the time differentiability actually can involve t equals to 0, as long as my uxt, as long as my initial condition is continuous. Okay, now my initial condition is not continuous. It's a bounded function that's only piecewise continuous. Okay, and you see here again, talking about the approaching to the initial condition, we're actually having a problem. Because of what? Because you see, my uxt is continuous. Because of what? It's actually, infinitely differentiable. So of course it is continuous. But when it is approaching, when time is going back to 0, my uxt, if it is approaching my phi x, that means that I'm actually using a continuous function to approach a not continuous function, a discontinuous function. Okay, and that is going to create a problem. So the argument is the following: the limit when t goes to 0, okay, my uxt will always become 1/2 of phi x plus, and then plus phi x minus. I'm going to explain what is meant by phi x plus and phi x minus. Here, phi x plus means the limit of phi when phi x 0 plus means the limit of phi when x approaches x0 on the right side, on the right hand. And phi x 0 minus means the limit of phi when x approaches x0 on the left hand. Or a little bit more clear is this. First of all, I said that now my phi x is actually a piecewise continuous function, right? If my phi x is a piecewise continuous function, that means that the whole line can be cut into many pieces, and on every piece, my phi x is continuous, right? Which means that there are actually many of the discontinuous points. So let's say here, if my x0 is a discontinuous point, then that means that here is going to be a left branch and here is going to be a right branch, right? And more specifically, this is going to be my phi x0 plus. This is going to be my phi x0 minus. Okay? Because this is the limit. This is the limit of phi when I am approaching on the right hand. This is the limit of phi when I'm approaching x0 on the left hand. That's good. So fx plus 5x plus and 5x minus. Well, then you might be asking, okay, what if x is just simply a regular quantity? What if there is no, because I wasn't saying that this formula only works for discontinuous points, right? What about a continuous point? What about continuous thing? Well, in that case, my 5x plus and 5x minus they will coincide with each other. It will be the same thing. So 1/2 multiplied by the two things. Okay, so this is going to be exactly 5x. Okay, this is going to be exactly 5x. So this theorem reveals that. Okay, what is the asymptotic behavior of the solution u when t approaches 0 actually depends on first of all where are the breaking points, where are the discontinuous points. If we are not on a discontinuous point, then my uxt will just simply approaches phi itself. If we are on a continuous point, on a discontinuous point, then uxt is actually approaching the average value of the units. Okay, the average value of the units. Okay, and actually the proof is also not really hard, and it's actually continuing exercises. Okay, it's actually continuing exercises, and the exercise of chapter 3.5. That's actually the question number 1 and question number 2. It's a very specific guidance about how to improve this. Okay, step by step. Okay, so yes, so that's everything about 3.5. Any question about 3.5? I'm going to finish with 3.5 for now. Okay, cool. So the last part, I'm having 20 minutes left. The last part, okay, of chapter 3.3, going back to chapter 3.3. So we'll be talking about the source on a half-line. So which means that again I'm talking about a diffusion equation with sources Vt minus kvxs, which equals to fxt. But in this case, my x and t, okay, my x actually belongs to only the half line, half of the real line. And of course, t is actually larger than 0. Okay? And of course, I'm now, because this is a diffusion on a half line, so I need to set up a boundary condition. The boundary condition is specifically V0t equals to ht. I'm not playing anything. I'm not playing any trick anymore, because you see, originally I was setting. Of course, this is still a Dirichlet boundary condition. This is still a Dirichlet boundary condition. It's directly about V, so it's not about any of this differentiation. But you see, originally I was selecting a very specific type of Dirichlet boundary condition, which was setting V, okay, 0t equals to 0. That's actually the simplest Dirichlet boundary condition, right? But now I'm just saying that it can be an arbitrary function of t. It's an arbitrary function of t. And the initial condition, again, of course, it's phi. Is my phi x. Okay. The reason that we are, what is the reason? Okay, what is the reason that we are able to make such a leap, okay, from a very specific type of Dirichlet boundary condition to a very general type of Dirichlet boundary condition? This actually covers every scenario, every possible scenario of the Dirichlet. Right? Okay, what's the reason? The only difference over here is that now we are dealing with a diffusion equation with sources. Okay, since we are already done with the discussion of the diffusion with the sources, we can now handle, okay, a much more general problem. Okay, a much more general problem. Or more specifically, okay, let's just say my specifically, okay? We are, let's just say let's use, okay, let's say W, okay, WXT, oh, probably not this level. X, and V, UVW, sorry, okay, let's say, okay, let's use that, okay, WXT equals to VXT, okay, minus HT. You see, the reasoning is again as before, right? I don't know how to handle this right hand side. I don't know how to handle this right hand side. I mean, this type of dirichlet boundary condition. But what do I know? What do I know? I know how to handle the dirichlet boundary condition when it is 0, right? Then if this is the only thing I know, then my thought is about, again, translating the new question into the old question to something that I know. How do we translate this? How do we translate the new boundary condition to the old boundary condition? Well, if the new boundary condition, if my V always satisfied that on the boundary is HT, then if I subtract HT everywhere, then of course, what is my boundary? My boundary is always going to be 0. And I exactly understand how do we set it, how do we deal with, okay, the old, the dirichlet boundary condition that is 0, right? Okay. But if my W is set, if my W is written in this way, what equation does my W satisfy? What equation does my W satisfy? So more specifically, what is my WT? XT. What is my WT XT? Okay, it should be VT XT and then minus H prime T. So far so good? So far so good? What is my VT XT?
KVXX.
It's actually KVXX and then plus
Oh, plus
FXT
FX.
minus H prime T. So far so good? So this basically tells us that, wait a minute. Yes, okay. And on the other hand, what is my WXX? Okay, what is my WXX? XT. What is my WXX? XT. This is my W, and taking into second order, 2 orders on space. Okay, VXX. This one goes away because it's not of S, right? So it equals to VXX XT. Okay, so that means that my WT exactly equals to K. Now, this VXX, okay, is going to be written into WXX, okay, and then plus FXT minus H prime T. Or a little bit more specifically, my W satisfies that WT minus KWXX equals to, okay, FXT minus H prime T. You see, this is exactly the reason that we are able to handle the more general type of dirichlet boundary condition. It is exactly because that we now know how to handle a inhomogeneous equation, right? Because if we didn't know how to handle an inhomogeneous equation, then that means that we always wanted to have to keep the right hand side, okay, to be exactly 0, right? Then that means that if I'm having some certain things like HT, then after subtracting the HT from the solution, okay, then the H prime T is going to stay there on the right hand side, which will again making this diffusion equation an inhomogeneous equation always with a source term. Okay, what we always use is source term. So is it good? Okay. Now, my WT, sorry, my VT is now rewritten into the WT, and my WT satisfy this new diffusion equation with sources, and my WT exactly satisfy that. My WT, my W0T, okay, my W0T equals to HT. Okay, so the question, oh sorry, not HT anymore. My bad, not HT anymore. Equals to 0 because HT is now subtracted everywhere. So now the question is, now what type of method that we can adopt to solve this diffusion equation and have a line? Again, it's 0.
We create W R.
Sorry?
We create W R.
We create W R. That's right. Okay. Well, actually, first of all, let's start from again. Let's start from phi naught. Well, okay. So sorry about that. Before that, okay, my Wx. What is my Wx0? What is my Wx0? Don't forget, my Wxt equals to Vxt minus Ht, right? Now, what about the initial condition? It has to be phi x, and then what? Because V, when t goes to 0, this guy is what? This guy is 0, right? This guy is, when t goes to 0, this guy is actually phi x. This guy is actually phi x. But nobody says that ht is 0 when t goes to 0, right? So the initial condition should also contain a negative h0 over here, okay? So this is the new problem. This is the new problem on half of the line, okay? And we'll be starting from first creating a, let's say, now my phi odd, first extending the initial condition, okay, to the whole line. Phi odd x, again, equals to phi x minus h0 when x is larger than 0, and 0 when x equals to 0, and negative phi, negative x, and then plus h0, okay, when x is smaller than 0. Then everything works for. Okay, everything works for. Sound good? Sound good? Okay. So this is it. This is it. And what about, so this is for the Dirichlet. This is the Dirichlet boundary condition. Okay. What about the Newman boundary condition? Newman boundary condition. Let's say my Vt minus KVxx, okay, and equals to Fxt. All the settings is the same, but now my V, the boundary condition is that Vx0t equals to Ht, and Vx0 equals to phi x. The boundary condition is about the first order differentiation, okay, instead of V itself. How do we deal with that? How do we deal with that? Again, this is something that we don't know how to tackle, but what do we know? What do we know about the boundary, or about the Newman boundary? What do we know about the Newman types of boundary? We know how to solve this question when my h is what? I know how to solve this boundary question when h is what? 0. If h is 0, then that means that my Vt, sorry, my Vx, okay, 0t, this guy is always 0. That means that I'm always dealing with something that is like this, right? And I will be able to reflect it along the y-axis. Okay. So I know how to tackle this question with h is 0, but unfortunately, it's not now not 0. But based on what we have just done, okay, to tackle the Dirichlet boundary condition, what do you propose to do over here? If we are subtracting, of course, we want to subtract something to that my Vx 0 equals to 0. But what do we need to subtract? Sorry? XHT. Why do you propose XHT?
Then when you do the partial x, you get ht.
That's right. Okay. So that means that now let's say my wxt equals to vxt minus xht. Okay. If we do this, then my wx at 0t will equals to, okay, vx 0t minus, okay, x ht x evaluated at x equals to 0. Okay? Which will become, okay, vx 0t minus here. Because the ht has nothing to do with x, so the differentiation over here is about, okay, so probably a better way to write this, should be something like, partial x. Okay, this is probably better information. And then minus ht. But by definition, this will be 0. This will be 0. Okay? And what about the initial condition? Like phi x 0. What about the initial condition? Okay. Well, when you see that is again phi x. It's again phi x, and with no extra term in it. With an extra term in it. And again, this is a Newman boundary condition, but now the Newman this new question satisfies that the Newman boundary condition is 0, which means that we'll be again able to apply our reflection concept. Okay. Cool. So yeah, so that's everything about chapter 3. Unfortunately, I didn't get to start chapter 4, but I think that's very good about it, and you should be able to do your homework right now. And next class, I plan to do the following. I plan to use the first half of the class to go through working 1, and I plan to use the second part of the class to take questions in homework and in anything that's unclear about the class notes. Okay, so for anything that's we could better utilize the time in the next class if we go back home and then try to generate a bunch of questions, okay, in the class. Then we'll be able to solve it, okay, and in the next half of the class. So that's everything about it. And thank you everyone for coming.